Meteor Artificial Intelligence is presenting. Intro to Transformers. We'll cover its origins, the innovative attention mechanism, and its unique architecture without convolution or recurrence. We'll conclude with transformative applications that highlight its revolutionary impact. Let's begin. Recurrent neural networks, or RNNs, have been at the forefront of sequence modeling, particularly in tasks like language translation. The advancements in variants like LSTM networks and GRUs pushed the boundaries of language processing, setting the stage for the next leap in AI. Traditional recurrent models process data sequentially, one step at a time. This inherent characteristic presents a significant bottleneck: they can't parallelize, which means they can't learn from multiple sentences simultaneously. Such sequential processing slows down training significantly. The attention mechanism introduces a new model paradigm that casts aside the step-by-step constraints of the past. It enables an attention-based approach, empowering the model to interpret entire sentences concurrently. This leap forward isn't just incremental, it's revolutionary, driving better performance and establishing new standards in language understanding. Seek-to-seek models, once the staple for machine translation, often stumbled with lengthy sentences and intricate dependencies. The integration of attention mechanisms has redefined their capabilities. Now, these enhanced RNNs can focus selectively on pertinent segments of input sequences, greatly sharpening understanding and elevating translation quality. The journey toward transformers began with the advent of recurrent neural networks, RNNs, which provided the first real breakthrough in sequential data processing for natural language processing tasks. Despite their pioneering status, RNNs were plagued by difficulties in handling long-term dependencies, leading to the development of more sophisticated variants. Long short-term memory, LSTM, networks and gated recurrent units, GRUs, were introduced to mitigate these issues, offering a significant leap in the model's capacity to remember information over longer sequences. The introduction of bidirectional LSTMs further enhanced the model's ability to understand context by processing data in both forward and reverse directions, a precursor to the more comprehensive approach that transformers would eventually take. In the wake of RNNs, convolutional neural networks, CNNs, began to make their mark on NLP. Renowned for their success in image recognition, CNNs offered a new paradigm with ByteNet and CONVS2S, which used parallel processing to increase efficiency. However, despite these advances, CNNs still struggled with long sequences, unable to fully capture the global context that is often crucial in language tasks. The limitations of both RNNs and CNNs in sequence modeling underscored the burgeoning need for an architecture that could understand and process entire sequences comprehensively and efficiently. As the field progressed, the ability to process and relate distant elements within a sequence became a significant point of contention for both RNNs and CNNs. The sequential nature of RNNs, despite improvements with LSTMs and GRUs, still limited the model's efficiency, particularly as the demand for parallel processing grew in the face of increasingly complex language tasks. The need for a more advanced model was clear, one that could efficiently handle long-range dependencies and offer a solution to the sequential bottleneck. This model would need to be capable of understanding sequences in their entirety, a challenge that would be boldly met by the introduction of the transformer. Let's discuss the attention mechanism. At the heart of the transformer model lies the attention mechanism, a pivotal innovation designed to address the fundamental challenge of learning long-range dependencies within sequence transduction tasks. Traditionally, the effectiveness of neural networks in these tasks was hampered by the lengthy paths that signals needed to traverse, making the learning process cumbersome. The attention mechanism revolutionizes this process by dramatically reducing the distance between any two positions in the input and output sequences, thereby streamlining the learning of these critical dependencies. As succinctly described by Vaswani and colleagues in their seminal 2017 paper, This mechanism allows the model to focus on the most relevant parts of the input sequence when generating each element of the output sequence, significantly enhancing the model's ability to handle complex transductions. Through this lens, the attention mechanism has not only simplified the architecture of neural networks but has also set new benchmarks in their performance across a vast array of NLP tasks. Unlike traditional models that process data sequentially, the attention mechanism operates on the principle of mapping a query alongside a series of key-value pairs to produce an output, where each component is represented as a vector. This architecture enables the model to compute the output as a weighted sum of the input values, with the weights themselves being determined through a compatibility function between the query and each key, as shown in equation number 1 below and in the original attention architecture on the left. Such a methodology ensures that the model pays attention to the most pertinent information in the input sequence when generating each part of the output sequence. Let's simplify the concepts of queries, keys, and values in the attention mechanism with a straightforward example. Imagine you're reading a book and come across the sentence, "The cat sat on the mat." We want to understand the importance of sat in this context. This might be representing the word sat if we're trying to understand how sat relates to other words in the sentence. The query is essentially asking what is relevant to sat in this sentence. Queries reflect our quest for knowledge. Keys could be all the other words in the sentence or certain features of these words that help to identify their role or relationship to the word sat. Each word acts as a key that the attention mechanism will use to determine how relevant it is to the query. For example, cat and mat would be keys. In a straightforward application, the values could also be the words themselves or some representation of them that provides more context about the sentence. The value associated with each key provides the content that we care about once we've decided which keys are relevant to our query. Let's put some numbers and calculate the attention for our example. First, we have embeddings for a small vocabulary consisting only of the words in our sentence. Each one is represented by a different 2D vector. As we focus on the word sat, Q4 sat is given by the vector 1, 1, focusing on action-related context. Keys are like tags for every word, indicating how relevant they might be to your focus. In our sentence, each word will have a key suggesting its relation to the concept of sitting. In our example, for simplicity, let's assume the vectors k and q are the same. The second action to take is to calculate the dot product scores, where our query vector, in the example, for focusing on sat is 1, 1. The multiplications result in a vector of 1, 1, 2, 0, 0. The third operation is scaling of the resulting dot product by the square root of the dimensionality of the key vectors. This scaling is done to prevent extremely large values in the dot product, which can lead to gradients that are too small for effective learning during the following softmax step. The fourth operation is the softmax application aims to convert the result into a probability distribution. This step essentially transforms the raw scores into attention weights that sum up to 1, indicating the relative importance or relevance of each item in the sequence with respect to the query. In our example, the score for sat is 0.4. The last operation is computed as a weighted sum of the value vectors, where the weights are the attention scores from the softmax step. The final output vector for sat is 0.7, 0.5. This vector is a weighted representation of the word sat in the context of the sentence, focusing more on itself and the word cat. This process demonstrates how the attention mechanism can dynamically emphasize certain parts of the input based on their relevance, allowing models to capture nuanced relationships in the data. In real-world applications, these calculations involve high-dimensional vectors and are performed for every word in the sequence, enabling the model to understand complex dependencies in a given context. In practical applications, the attention function is applied to a collection of queries at once, which are consolidated into a single matrix Q. Similarly, keys and values are grouped into matrices K and V, respectively. Let's present the multi-head attention. This method innovates beyond the traditional attention mechanism, which utilizes keys, values, and queries of a uniform model dimension. Multi-head attention diverges by projecting these elements into different dimensions multiple times through unique, learned linear projections. This isn't merely an expansion but a deliberate strategy to diversify attention across various dimensions. The mechanism then processes these projections in parallel, each generating different output, thereby enriching the model's processing capabilities. The benefits of multi-head attention are profound. It allows the model to simultaneously focus on distinct representation subspaces and positions, offering a comprehensive view of the information. Traditional single-head attention mechanisms might average out critical nuances, but multi-head attention maintains and emphasizes these distinctions. After delving into the intricacies of the attention mechanism and the multi-head attention, it's now time to introduce the transformers. The idea was published in an amazing paper named Attention is All You Need by Vaswani et al. In 2017. The transformer architecture reveals a sophisticated encoder-decoder structure at its core. This design paradigm, fundamental to many leading neural sequence transduction models, serves as the backbone for the transformer. In this architecture, the encoder's role is to convert an input sequence of symbols into a series of continuous representations. These representations then serve as the foundation upon which the decoder constructs the output sequence, symbol by symbol, in an autoregressive manner. This means each new symbol generated considers the entirety of the symbols produced thus far, ensuring each step is informed by the previous. What sets the transformer apart is its utilization of multi-head attention blocks within both encoder and decoder layers. This allows for simultaneous processing of multiple sequence positions, granting the model an unparalleled ability to capture complex dependencies and nuances. By referencing the image on the right, we see a visual representation of this architecture, highlighting the transformative approach of using stacked self-attention and fully connected layers to achieve remarkable sequence transduction outcomes. Let's delve into the encoder and decoder separately. In the encoder's design, a stack of n equals 6 identical layers forms its backbone. Each layer encompasses two essential sublayers. The first sublayer is a multi-head self-attention mechanism, allowing the model to capture intricate dependencies within the input sequence. The second sublayer takes the form of a position-wise, fully connected feed-forward network, further enhancing the model's ability to process and transform data. To foster seamless information flow, residual connections are introduced around each of these sublayers, optimizing the learning process. Moreover, layer normalization is applied to stabilize the outputs of each sublayer. The decoder architecture mirrors that of the encoder, with a stack of n equals 6 identical layers. However, the decoder introduces an additional sublayer, making a total of 3 sublayers in each decoder layer. While the first 2 sublayers resemble those in the encoder, the third sublayer performs multi-head attention over the output of the encoder stack, enabling the decoder to attend to relevant information. Like the encoder, the decoder employs residual connections around each sublayer for optimized information flow. Layer normalization is also applied to ensure consistent output stability. Notably, the self-attention sublayer in the decoder is modified to prevent positions from attending to subsequent positions, ensuring that predictions for a given position solely depend on known outputs at earlier positions. In the layers of transformers, the crucial component known as encoder-decoder attention. Here, queries are generated from the previous decoder layer, while the memory keys and values are obtained from the output of the encoder. This design empowers every position within the decoder to have the capability to attend to all positions within the input sequence. Transformer models, which lack recurrence and convolution, preserving the order of tokens within a sequence is essential. By incorporating positional encodings into the input embeddings of both the encoder and decoder stacks, a crucial information about the relative or absolute positions of tokens in the sequence is provided. The choice of positional encodings is versatile, but a notable recommendation from the groundbreaking work, Attention is All You Need, involves using sign function with varying frequencies. In the equation below, POS represents the position and I represents the dimension. To validate the effectiveness of the proposed transformer architecture, The authors conducted experiments using a translation model on the WMT 2014 English to German task. This evaluation yielded an outstanding BLEU score of 28.4, establishing a new state-of-the-art benchmark. To put this achievement into perspective, the previous CONVS-2S model achieved a BLEU score of 26.36, making the transformer's improvement quite significant. Additionally, it's worth noting that the transformer achieved this remarkable result with a training cost that was less than 1/4 of the time compared to CONVS-2S. BLEU, Bilingual Evaluation Understudy, is a metric commonly used for machine translation evaluation. It measures the similarity between the generated translation and reference translations, with scores ranging from 0 to 100. There are some challenges and limitations using the transformers. Let's mention some of them. Transformers demand significant computational power, limiting their use to those with access to advanced hardware. The high cost and complexity of training transformers restrict their use to well-resourced organizations. Transformers' performance hinges on large datasets, posing a challenge in data-scarce environments. The inner workings of transformers are complex and opaque, making their decisions hard to interpret. The growing size of transformer models complicates their deployment and maintenance in resource-constrained settings. Updating transformers with new information efficiently remains a challenging and resource-intensive task. Transformers, what next? As we step into the beginning of 2024, we reflect on the monumental advancements in transformer technologies and their applications that have reshaped our interaction with machines. BERT has revolutionized our system's understanding of context in text, making our machines more intuitive and our conversations with them more meaningful. The GPT series has taken text generation to new heights, allowing for creative and complex generative capabilities that can mimic human-like writing. Vision Transformer, or VIT, has successfully translated the power of transformers to the realm of image classification, setting new standards for machine perception. DALL-E has blurred the lines between text and imagery, enabling the creation of new visual content from textual descriptions, sparking a revolution in creative AI. And now, the newest breakthrough on the horizon for 2024, ROPE, or Rotary Position Embedding, which leverages positional information in a transformative way that promises to unlock even more potential from the transformer architecture. What will this mean for the future of AI? Thank you for watching. You are invited to visit our website and follow us. Meteor Artificial Intelligence.